Yes, thank you for the introduction. Today I will present the evaluation methods of adhesively bonded double cantilever beam tests using optical fiber strain measurements. So first I will give a small motivation, then a quick insight into my test setup. After that, I will come to my main part, which will be the proof of methods. And at the end, I will summarize and give a small outlook. Adhesively bonded joints are typically modeled using traction separation relationships as constitutive laws. However, on the way how these energy-based methods are used, you usually get the traction separation law only on the crack tip, initial crack tip position. So our goal was to get more data. So we wanted to get more traction separation laws out of one test, and invented a method to get the traction separation laws throughout the whole beam using these optical fiber strain measurements. So here you can see typical test for the J-integral method, where where you measure the force, the rotation, and with, in this case, a DIC, the crack tip opening displacement. After that, using the equations below, you can calculate the cohesive traction. In our case, we used an optical fiber measurement to calculate the strain. As my supervisor said before, we get the strain at each position of the beam. And with that, we get the curvature using beam theory. Oh, I see there is a square missing in the GOF equation. Using beam theory, you get the moment, and with that, the energy, and eventually get, when you derive with respect to the separation at each position of the beam, the traction separation law at every position, not only at the initial crack tip. So we used a mode 1 DCB test with a structural adhesive. I combined both of the setups I showed before. We used 2 inclinometers to measure the rotation, a load cell for the force, and additionally a DIC for the initial crack tip separation, and the optical fiber. So on the left, you can see how a typical test result, a good test result would look like. On the right, you can see how some test results were looking like. Sometimes you get partly unevaluable test results where you only can evaluate one beam or only some of the time steps, but usually we get the left ones. So we assume that the maximum of the strain in this case, the minimum of the strain gives us the current crack tip position. And after that, we can evaluate the fracture process zone. So now I give a small insight into the proof of my methods, because I wanted to check if it is really the crack tip position we get, and if we are allowed to get the traction separation laws from at every position of the beam. So first, on the left, you can see the curvature over the position of the beam. Each curve is at a different time step. And if you evaluate the maxima, you can see that the crack at first isn't growing, and after that, you can see crack propagation. So I used a corrected beam theory approach and plotted the cube root of the compliance over the crack extension I got from my results. Did a linear fit, extrapolated it, and was able to get the correction factor delta. Then I used 2 different approaches for the simple and the corrected beam theory to check if I get the same results. And on the right, you can see the crack position over the time. In blue, you see the crack position I got from my optical fiber measurement. And as you can see, the corrected beam theory is basically the same. So after that, as I said before, I also measured the crack tip opening displacement with the DIC. So I wanted to check if this is also the same by integrating the curvature 2 times over the time at the initial crack tip position. And as you can see on the left, the mode 1 separation over the time looks the same basically. So now I wanted to check for the energy release rate and the traction separation loss. On the right, you can see the mode 1 energy release rate. The gray lines are all my curves from my optical fiber measurement with kind of a big scattering. This is why I evaluated the mean, which is the red curve, and the transparent area behind it is my standard deviation. The black curve is my external measurement, which is from the DIC and the external force and rotation measurements. Especially in the crack tip, you can see that we get quite similar results. But there's one problem. For the traction separation law, we need the cohesive stiffness, we need the energy release rate, and also the maximum separation. And since we have a constant slope, you will see later on that we can't evaluate the cohesive stiffness from this. So what we used was the method of the Winkler elastic foundation. And if you take the Anders function and derive it 2 times, you get basically the curvature. So we were able to fit this onto our curvature we get from the optical fiber. And which was even more, which was very nice, was that we can get the initial guesses directly from our measured data. And with that, you get the lambda. With lambda, you get the cohesive stiffness. And when you integrate the data 2 times, you get your basically the deflection, which is if you multiplicate it by 2, you get the separation. So now these are the traction separation laws, which I got by deriving the previous ERR curves. The gray curves is my data, which I separated into 2 parts. So A is the crack initiation and B is the crack propagation. Just because I had so much scattering, I wanted to check if there's any problem in the beginning. But as you can see down there, the data was, I mean, it was different, but it was okay because of the big scattering. The black curve is the external measurement. The blue lines is the cohesive stiffness I got from the Winkler elastic foundation, and the purple interval is the maximum separation I got from integrating. So now I have a lot of statistics from one test, but after that I wanted to do some more tests. So I did 2 more tests with a different initial crack tip position and wanted to check for my 3 parameters I need for my traction separation law. So as you can see, for the cohesive stiffness, I get basically the same results. Same for my maximum separation. The external measurement, I just brought up a criterion for myself, which I used. I used 5% of the maximum stiffness and said at that point, there's basically the breaking point. And for the ERR, I get also quite similar results. Yes. So quick summary, I got about, from one test, I got about 700 to 750 TSLs, from which I was able to use about 650. So all in all, I got over 2,000 to 3,000 TSLs from the 3 tests. I had good results with the crack propagation. And yes, the outlook, I want to simulate the results, but I think I need to think about what's the next step. Thank you very much.